7:01, and I guess we can start, right? So at this point, okay, in the previous class, we finished discussing central forces. Enough of those central forces. And now back to formalisms. And today we will start developing Hamiltonian formalism, right? Which is, yeah, as I told you at the very beginning, there are three formalisms, right? Newtonian, we discussed that in undergraduate level course. Then Lagrangian formalism, we have developed that at the very beginning, and now it's time for the Hamiltonian formalism. But before we start introducing Hamiltonian formalism, again, let me repeat. So, what's the major goal? Why people were kind of driven to introduce this Hamiltonian formalism in the first place? What was the goal, right? Because there's nothing seriously wrong with the Lagrangian formalism. We achieved almost everything that we wanted in an attempt to move from the Newtonian formalism, right? What we didn't like in Newtonian formalism, that you have to deal with vector quantities, right? And the form of the Newton's second law keeps changes as if you change coordinate system, right? More difficult to deal with constraints. And Lagrangian formalism solved all those problems, right? So you deal with only energies, great. Form of the Lagrange equation exactly the same. It doesn't matter where you go in terms of new coordinates. And basically every time you just basically bypass the constraints, right? If you use classic, typical Lagrangian formalism, not Lagrange multiplier, right? So why do we want to develop a new formalism? And the major goal is Lagrangian formalism is based on the fact that we treat q's and q dots, generalized coordinates and generalized velocities, as independent variables, right? But if you go to quantum mechanics doesn't accept generalized velocities, right? It doesn't work with velocities. It works with momenta, right? So it means that in order to use formalism similar to, or if we want to use Lagrangian formalism, we need to kind of adjust it, change it, right, so that we can use it in quantum mechanics. And the major thing that must be improved, we just need to get rid of q dots in the formalism and introduce momenta, right? So basically, that's one of the major that's the major reason why Hamiltonian formalism was introduced, right? Otherwise, Lagrangian was great. Why? Why would you introduce something new? Okay, so now, after this introduction, let me just sort of like a juxtapose these two formalisms in order to sort of compare them, right? And then we will start deriving Hamilton's equations, but first in a kind of sneaky way by moving from the Lagrangian formalism to the Hamiltonian formalism. We've done in a similar way. We introduced Lagrangian formalism in the previous semester in undergraduate level course, right? So we started with Newtonian formalism and then did some manipulations and introduced Lagrange equations, right? In a finicky way. And now we're going to do similar, right? And again, it's good probably from educational point of view, right? But then, of course, at the end of today's class, most likely we will derive Hamilton's equations from the first principle, from the foundation, as it should be done all the time in any theory, right? So you grab some foundation and derive whatever is needed, right? Okay, but first, let's sort of summarize both of these approaches. And probably I will write something like this. First of all, it's chapter 8. And let me write Hamiltonian formalism. Hamiltonian formalism, right? And so let's just say we have some arbitrary system of n particles. Let's say arbitrary system with n degrees of freedom, right? So let's say we have a system with n degrees of freedom. Right. And for this system, I just want to write everything that we know about the Lagrangian formalism, and here the future stuff which we're going to develop for the Hamiltonian formalism. Okay. Okay, let me write here. So this will be our, yeah, why not? So Lagrangian formalism, stuff related to the Lagrangian formalism, and here stuff related to the Hamiltonian formalism. First of all, they share the same foundation. Hamilton's principle, it's exactly the same, right? Basis is exactly the same, right? So foundation, right? Foundation, Hamilton's principle, Hamilton's principle. And you see I'm writing it in the middle because it belongs to both of these approaches, right? So they share the same foundation. And as I said, closer to the end of the class, we will derive Hamilton's equations from this principle, right? Then, in the Lagrangian formalism, we know that mechanical state of the system can be described by Q and Q dots, generalized coordinates and generalized momenta, right? And of course, in the Lagrangian formalism, we treat them as independent. Very, very important, right? So let me write in the middle, mechanical state of course, any system is described by, and over here it will be qi dots, right? That's what we need to introduce, right, in order to describe the system. And it's very important, we treat them as independent. All right. Okay, probably I will write linearly independent. Linearly independent. And in the Hamiltonian formalism, instead of Q dots, we're going to use generalized momenta, right? Over here, we're going to have what? Qi and Pi, and we're going to treat them as linearly independent. And actually, we treat them as independent up to the point when we write down equations, first order or second order differential equation, right? And when we have a bunch of equations, right, because usually we have n equations, right? Then, of course, you will realize, okay, this r dot, it's a derivative of r, and then, of course, you start combining equations, but up to that point, we treat them as independent, right? Okay, so, of course, this is important, right? And then, of course, in the Lagrangian formalism, we introduce Lagrangian function, right? If you know the Lagrangian, you know everything about the system. The rest is just a calculus, the question of just getting through the mathematics. And of course, it's a function of qi dot nt. And here we're going to have Hamiltonian, which will be a function of qi, pi, nt. And again, what is interesting relative to the Newtonian formalism, we don't have to introduce Q double dots, right? So we have Q and Q dots, and it's enough, right, to describe the state of the system. All right, and of course, here the equation of motion, it's a Lagrange equation, right? So partial derivative of L with respect to Qi equals to d over dt, and partial derivative of L with respect to Qi dot. Lagrange equation, and we have n, I runs from 1 to n second order differential equations. So we have n second order differential equations, right? So we have n second order differential equations. But in the Hamiltonian formalism, we're going to have slightly different situation. From one side, kind of easier, but from the other side, kind of more difficult. So the Hamilton's equations are going to have this look. Qi dot equals to partial derivative of the Hamiltonian with respect to pi. Of course, we will derive them. Right now, I just want to show everything on the same whiteboard, right? And then pi dot equals to minus partial derivative of h with respect to qi. So Hamilton's equations, how many of those we have? We have n equations, these, and n these. As a result, we have 2n but first order differential equations. So from one side, we reduce the order of the equations, the differential equations, from the second to the first one. But at the same time, we increase their numbers, right, to 2n. So from one side, it's advantages. From the other side, it's a disadvantages kind of dealing with more equations, right? So it depends. We will see probably next class. We will discuss when this approach is better than this approach. Again, if we, for example, restrict ourselves only to classical mechanics, we're not talking about quantum mechanics. So we will discuss when that approach is easier, slightly easier relative to this, and when this approach is easier than that, right? So, but anyway, so let me write first here that these are no, 2n first order differential equations. Easy equations, but larger number of equations, because again, at the end of the day, you need to get 2n constants of integration. It doesn't matter which approach you use, right? Okay, let me separate. Right. And of course, maybe I should add, of course, this approach is, of course, very useful in quantum mechanics, right? So this is useful in quantum mechanics, statistical mechanics also, right? But we're going to apply them only in classical mechanics. Okay. So again, the major difference that we need to get rid of q dot and introduce p. And that's basically the kind of not a completely twin formalism, but since they share the same foundation, it means they have lots in common, right? Okay, so now as a result, let's derive these equations, but first kind of from the Lagrangian formalism. So let's assume that we have some, of course, the system, right? Some Lagrangian is given, right? Okay, you know what? Let me put a new bullet, right? And I'm thinking, should I write something or just start deriving? Okay, let's write. Let's get Hamilton's equations. From now on, again, Hamilton's name will be almost everywhere. At some point, you feel like dizzy, right? Hamilton this, Hamilton that, Hamilton is everywhere, right? It's okay, Hamilton's equations. Okay, these guys. But again, as I said, first it's good actually from educational point of view when you move from something which you know to something which you don't know or something which is new. So that's what we do now. So let's look at total differential of the Lagrangian, which is of course a function of q dot, and t, right? Okay, so strict mathematical procedure. So and I'm going to write it like this: partial derivative of L with respect to qi and dqi. Usually we write here summation, or maybe, you know what, let me write at the very beginning and then I will start omitting it. Of course, here there should be summation over I. But of course, let's use tensor notations, right, which you're familiar with, right? Whenever you see two subscripts, exactly the same subscripts, it basically means that summation is assumed, tacitly assumed, right? So from now on, I'm not going to write this summation, I'm going to omit, but whenever you see I or JJ, it means that summation is assumed, right? Tensor notations we're going to use. Right? So let me emphasize that from now on, I will omit this. And we're going to use tensor notation. Okay, so then, of course, the second term is going to be plus partial derivative of L with respect to Qi dot dQi dot, right? And then, of course, partial derivative of L with respect to T and dt. Right, now, right now we're still in the Lagrangian formalism, and of course we can use Lagrange equation. Lagrange equation, you remember what is this, right? It's a generalized momentum, right? Generalized momentum, and of course this as a result, it's a time derivative of a generalized momentum. So we can use it here, right? So it means that dl over dqi dot, this is pi, and of course as a result this is pi dot. Right. Okay, let me rewrite so to make it look simpler, and then of course, and then we will try to understand what needs to be done. All right. So it will be pi dot dqi plus pi and dqi dot and plus partial derivative of L with respect to t dt. Okay, so now what should be the next step logically? We want to get rid of q dots and introduce p's as linearly independent, right, variable. And look, we want to have variations, and you will see at some point why. I want to have not variations, dq, right, differentials of independent variables, right? This is good, so that's what we will have at the end in the Hamiltonian formalism, but dq dot is not good. Right, I want to get rid of this dq dot and introduce somehow dq, because q's and p's are going to be linearly independent in new formalism. Again, you remember we're moving to the new formalism, right? All right, let me emphasize. So, need to get rid of this, right? So we need to remove it, right? Okay, so, and of course that can be easily done. Yeah. Because if I, for example, take a differential of pi qi dot, right? So I can write it like this. So it will be qi dot dpi and plus what? Pi dqi dot. And so which part we need in our equation? Pi dq dot. So this. So we just need to plug it, and of course we can easily do this. Of course I will have to move to that side of the whiteboard. Right. So it will be pi dot dqi, and instead of this I will have what? This go to that side with minus, so it will be positive d plus d differential of pi qi dot and minus this term minus qi dot dpi, right? And that plus partial derivative of L with respect to t dt. Great. It looks promising. And now here we have total differential, and here we have total differential. Let's combine them. And we're going to combine them on that right-hand side. So I'm going to write like this. So it will be differential of, all right, pi qi dot. And again, of course, you remember we're using tensor notations. Here, tacitly, we assume summation over I. You see, I. So here, everywhere except for there, we have summations over I, basically, right? So this minus that, minus Lagrangian, right? And of course, the rest of the terms will go to the other side with opposite sign, right? Goes there, right? And these guys will be, so I will start with this guy. So it will be qi dot dpi and minus pi dot dqi and plus partial derivative of L with respect to time dt. Okay, so now we constructed something new. Let's give it a name, nice name, right? And we're going to call it Hamiltonian, right? So let's, it's H, right? Hamiltonian. And differential of that has the right structure. Q's, P's, right? So which we want to treat as independent, right? Okay, so now let me write down. So H, right, will be called, which way I wrote it? Okay, with, okay, Q, PT equals, okay, I can put 3 lines, so it will be, okay, and you know what, I will put summation now, since basically now I want to write sort of like a definition, how we introduce it. I wrote summation, so it will be pi qi dot minus L, right? Okay, let me frame it. And call it Hamiltonian. Okay, you might, it's possible that you recognize what is this. Basically, just now we derived what is called Legendre transformations from calculus, right, or from mathematical analysis or whatever course you had, right? It's a Legendre transformations. Typical procedure of replacing one variable in the function with another one. Let's say, in this case, what we do, we replace q dots with p. And the procedure is typical. You take the product of the variable which you want to remove from the old function, multiply it by the variable which you want to introduce in the new function instead of the old variable. So you see product, q dot p, old variable, new variable which we want to introduce, and minus the function, the old function itself. It's a typical Legendre transformation. You can replace any, let's say you have function y, which depends on, I don't know, x and t, right? And then you have function, you want to introduce function z, which you want to depend on, I know, u and t. So you just take a product of the old variable, which I wanted to remove, I forgot, right? Let's say x and t, multiply them, and then minus the value of, okay, not the value, and minus the function, the old function, right? Typical Legendre transformation, right? I can write also, it's we can call it Hamiltonian or Hamiltonian function. It doesn't matter. So what else? Yeah. If you remember in chapter 2, we've done something similar when we discussed conservation of energy, right, in the Lagrangian formalism. And after similar manipulations, we ended up with something similar, and we introduced what is called the energy function. And you remember back then I told you, guys, maybe in a few weeks, we will introduce Hamiltonian in a very similar way. and this is the moment. So we're introducing now, instead of energy function, we're introducing Hamiltonian. What's the difference between that energy function and the Hamiltonian? And the difference is very simple. Energy function depends on q dot and time. Hamiltonian on q, p, and time. Right? Okay, but let me emphasize on that, right? Remind you. Maybe sort of like a small bullet. Similarly, we introduced the energy function. The energy function which was, okay, let me say chapter 2. And the energy function we introduced like this. So it was the function of q's, q dot, and t, and we introduce it like this, right? Summation of qi dot dl over dqi dot and minus l. dl over dqi dot, it's our generalized momentum. So basically what we have here p times q dot minus l. So this and that, I don't want to say identical, but close to that, right? The only difference that in Hamiltonian, q dot is replaced with p, right? All right.
Professor, I have a quick question. So in the second to last line where we did dpiqi dot, we moved it over to the left-hand side, right? So now it's d of l on the next whiteboard.
Hold it. Minus dl over dt. Yes. I was afraid about pluses and minuses in these first terms, but I forgot to change in the last one. Yeah, absolutely correct. Thank you. Right. In a few minutes, I would realize that when I would start writing down Hamilton's equations. But yeah, thanks. Absolutely. I changed pluses to minuses and minuses to pluses in all terms except for the last one. I think in all terms, right? Yeah. Still checking. Right. No, I didn't change. Right. So this should be with.
So it's just
no.
that.
No, not here. Over there.
Yeah.
At this point. Okay. So and then at this line I started moving terms around. So that's this term with plus, that with minus and minus. Yeah, now it's all good. Right. Great. Right. Okay, so differences. Okay, let me emphasize. So differences is h is a function of q, p, and t, and energy function is a function of q dot, and t. Right. Okay, just a small digression. And of course now I just wanted to compare, of course, these two functions because it can trigger questions. And now back to this. So we introduced this h, and of course now we need to get Hamilton's equations, right? At the end, of course, h is a function of q, p, t. So now let's write down from the other side. Okay, so that's digression. So now from the other side, I can write, since h is a function of q, p, and t at the end. What do I mean? So we got this moving from the Lagrangian formalism, right? Doing all these manipulations, right? Moving from the Lagrangian side. But at the end, from the other side, from our goal, right? So h must be a function of q, p, and t. So now just from the mathematical point of view, let's write down differential of what we want to get at the end. And then sort of compare that result which we achieved moving from the Lagrangian approach and the differential of Hamiltonian, since we know what we want. So dh, which is a function of q, p, and t, so I can write, again, summations will be skipped, dh over dqi, dqi, right? Partial derivative of h with respect to qi times dqi, then plus partial derivative of h with respect to pi, dpi, and plus partial derivative of h with respect to t dt. And so now we can compare, kind of compare, I don't like the words compare here, but okay, it's this and this, right? So strictly speaking, I should say this, since q's and p's are linearly independent, so this can be equal to that only when this factor equals to this factor, right? Because again, q and p are linearly independent, so this factor must be equal to that, and this must be equal to that. Only in this case, this equals to that. That's why I said I don't like to say the word by comparing. No, I just have to pronounce the properly. Since q and p are independent, so the corresponding factors must be equal. Okay, so since q and p are independent, and of course differentials are also independent, so we can write that, as I said, these must be equal to that, right? So yeah, so as a result we're getting qi dot this equals to a partial derivative of the Hamiltonian with respect to pi. So first set of Hamilton's equations, this one. And now the second, this must be equal to that, and here there is a minus, right? So now we're getting that pi dot equals to minus partial derivative of h with respect to qi, second set of the Hamilton's equations. And we still have additional part, dh over dt and dl over dt. At this point, I would realize that something is finicky, right? That the minus is missing, right? But up to this point, I doubt that I would see it immediately. So now I can write that a partial derivative of the Hamiltonian with respect to time equals to minus partial derivative of the Lagrangian with respect to time. Right. Correct? Everything is, yeah. Okay, so these two equations are equations of motions. They're going to give us evolution of the system, life of the system, right? And very often they're called canonical equations. Canonical usually means the simplest possible form and symmetrical. If something has the simplest possible form and kind of, in this case, even almost symmetrical, except for that minus, everything would be great, right? But minus kind of spoils everything, right? So it's called canonical. It's like canonical equation of an ellipse. It's the simplest possible equation, right? Only in special coordinate system, and that coordinate system is called canonical coordinates, right? All right. So let me write. So it's a, again, of course, there are n of these, n of those. So we have 2n canonical equations of Hamilton. 2n canonical equations of Hamilton. Oh, just Hamilton's equations. And yeah, this word is kind of important, canonical. All right, in a couple of classes, we will start developing canonical transformations. We will try to move to nice places, right? But of course, we will talk about that in the future. So that's why I'm emphasizing on this canonical, that these equations are called canonical. So, yeah, and of course, this compares explicit time dependence of the Hamiltonian in QP space with explicit time dependence of the Lagrangian in Q dot space, generalized coordinates, generalized velocities, right? And what is great, so if you have Lagrangian initially, and if you see that, for example, Lagrangian doesn't have explicit time dependence, you can tell immediately, you can immediately foresee the future. You can tell immediately that Hamiltonian, which you, for example, want to get, is not going to have explicit time dependence, right? So it just compares explicit time dependencies. So if Lagrangian is cyclic in time, then of course Hamiltonian is going to have the same dependence on time. Okay, so that's what I wanted to discuss in this point. So again, just useful from the educational point of view to move from what we know to something new. But of course, from the mathematical point of view, no, not from the mathematical, from the point of view of theoretical physics, we should get this from the first principle, from the Hamilton's principle. And we're going to get that probably closer to the end of this class. All right, okay, so now let me describe the procedure that we have to make in order to get Lagrangian function, Hamiltonian function out of the Lagrangian function. Assuming, and quite often we will start writing down Lagrangian first, and then make a transition to the Hamiltonian. Right? Although in quantum mechanics, probably you've seen it already, right? So very often, just in quantum mechanics, they will tell you, okay, here's the Hamiltonian, let's use it, without any justification why it is so, right? And because quite often it's next to impossible to get the Hamiltonian. They just fudge it somehow, create it somehow, and then use it. Okay, so now I still have space. Probably I'll try to fit it here. So I will put a new bullet and write how H can be constructed, or how can H be constructed. So how can Hamiltonian H be constructed? Right. Question mark. Right. So 3 steps. Actually, we're going to introduce 2 methods, approaches how to get Hamiltonian out of the Lagrangian. So of course, first you need to construct Lagrangian. Construct the Lagrangian function. Second, of course, at some point you will have to write this, but before writing that, you need to prepare ingredients, because you need to remove all these q dots. Of course, q dot is here. Also, q dot is in the Lagrangian, right? So you need to prepare some equations which can be used to remove q dot from this, right? And so where can we get those equations? From the from the definition of generalized momentum. Generalized momentum, yeah. So I can write, so pi equals partial derivative of the Lagrangian with respect to qi, and of course Lagrangian depends on q dot and t. I just wrote down definition of generalized momentum, of course, right? And why this equation I want to use? Because we have here p, here we have q dot. So we can solve it for q dot, and as a result, it will be q dot will be written in terms of q and p, and that's what we want. We can grab that inverted equation and we can shove it over here and there to get rid of q dots, right? Okay, so from here, by inverting, if you invert this equation, you will be able to get q dot equals to q dot as a function of q, p, and time q, p, and time. So every time we will have to use this definition of generalized momentum in order to prepare the replacement. And after this, yeah, we need to shove. But before, okay, I should have mentioned before I started writing steps. When the Hamiltonian is not completely ready, when the Hamiltonian is still written in terms of q dots and p, sort of like it's still in the transition to the final form, when the Hamiltonian still depends on q's, q dots, right? That Hamiltonian is called pseudo Hamiltonian, or half-cooked, like my professors used to call it, right? Half-cooked Hamiltonian, pseudo Hamiltonian. But once you removed all generalized velocities, only then you can call that as Hamiltonian, right? Maybe I should have mentioned it, but okay, I will write it underneath. Right, and so the step number 3, of course, we need to use this, right? So h equals to, okay, so my way, so it will be summation of qi dot pi minus Lagrangian, which is a function of qi dots and t, right? And yeah, as I said, now we need to take this prepared equation. Actually, this inversion can be sometimes complicated, right? It depends, of course, on the situation. And this can be plugged over there, right? And after this, we will get, of course, the final Hamiltonian. And about the terminology, so let me write down. So pretty much the procedure is done, right? So I just want to digress a little bit and emphasize. So when Hamiltonian is a function of still q dot and t, so that you haven't completed the transformation, the procedure. It's called pseudo Hamiltonian, and very often tilde is added on top. A pseudo Hamiltonian. Right. But once you replace q dots with p, yeah, so at that point, it's final product. Okay, so this is the first method. Okay, maybe I can, right? So it's method number 1. Now let's say a few words about method number 2, which is a little bit shorter. Right. Okay, let me check if I mentioned everything. Yeah, it looks like. And I need to start invading this part of the board. Let's see if I need this. No, we will have to get all this actually. Right, second. So that was number 1, and now second. Okay, let me emphasize method. And we're going to use stuff which we derived for the energy function in chapter 2. You remember when we discussed introduced first energy function and then tried to get conservation of mechanical energy, right? So we made some assumptions in order to prove that after assuming those after those assumptions, we show that energy function is kinetic energy plus potential energy, which is total mechanical energy. We've done it, right? So now we can just recycle those results. We can reuse those results. But now, of course, and can be used discussing Hamiltonian, right? Okay, so let me write something like this. All right. So since what h is almost the same as Hamiltonian, right? Then we can use, right? We can recycle results from chapter 2, right? Okay, and now let me remind you those assumptions and those, actually the results I told you, but the assumptions. The result is that under certain conditions, energy function, and in our case Hamiltonian, is just a kinetic energy plus potential energy, which is total mechanical energy. So those assumptions. First, forces acting on the system should be conservative. So we can introduce potential energy, and potential energy should be function of positions only. It shouldn't have any generalized velocities, right? And the second condition, okay, I will write them down. And the second, if transformation equations are time independent, right? You remember it's a chapter 1. At the end of the chapter 1, we discussed that general form of the kinetic energy. So if transformation equations are time independent, then kinetic energy has a quadratic form, right? So these two, if these two statements are correct, then energy function and now Hamiltonian can be written as total or equal total mechanical energy, T plus U, or V, we used V potential energy. So let me state this. All right, so results from chapter 2, and so first part of that first assumption, V is not a function of generalized velocities, right? Basically, the system is conservative. I can write, or we can write forces are conservative, right? So that was the first part, the first assumption. And the second, right? So transformation equations are time independent. Transformation equations are t independent. You know what? I can probably, no, let me save that space. T independent. Basically, we can write that Ri equals to Ri, a function of Q1 and all the way to Qn, but no time dependence. No time dependence. I feel like soon I will have to change my marker. Losing slowly contrast, but still decent. And of course, as a result of this, immediately we can write, it's basically like you can state either this or the second, because the fact that kinetic energy has a quadratic form, it's a direct consequence of this statement. Right? Or I can say that kinetic energy in this case equals to what? Let me write this for my notes. It's something like this, JK. We derive it in chapter 1. Qj dot Qk dot. Quadratic form. Kinetic energy has a quadratic form. All right. Okay, I will probably write underneath. Kinetic energy has a quadratic form only. Okay, so what it means, again, usually we start from the Lagrangian, right? So you write down the Lagrangian as I wrote, right? And then you look at the Lagrangian. If potential energy is nice, right? No dependencies on the velocities, and most of the time it is true. And then if you see that kinetic energy has a quadratic form only, or if you had, okay, conservation of brackets, right? Or if you even have access to transformation equations, you can look at the transformation equations if they are time independent. So if these two statements are correct, then you can write down immediately that Hamiltonian equals to kinetic energy plus potential energy. Right? So if this is true, then you can write that Hamiltonian equals to what total mechanical energy equals to kinetic plus potential energy. As a result, it simplifies transformation or transition from the Lagrangian to the Hamiltonian slightly, maybe like in one line, right? Right. So that will be the second approach. Let me frame it, of course. So in this case, it will be easier. Slightly shorter approach. Right, slightly shorter, because in this case you wouldn't have to subtract terms over here, like here, right? So that's the that's where you can save, I don't know, a step or half a step, right? Okay, so we will look at this, all right, at the example. All right, and now, before we start looking at the example, so again, method number one, method number two, right? Before we start looking at the example, simple example at the very beginning. Now also let's get conditions under which Hamiltonian is also Hamiltonian is a constant of motion. Hamiltonian is a constant of motion. Right. So now let me add something. A new green bullet. Let me add green bullet, right? When is h a constant of motion? Basically, when is it conserved, right? And of course, if also this is correct, then Hamiltonian is a total mechanical energy and constant, right? But first, let's finish this, and then of course we can combine these results. Okay, so now let's look at the dynamics. If we are interested, if we are interested in the conditions when this is the constant of motion, let's see what happens with h in terms of time. Let's look at the total time derivative, dh over dt, and of course h is a function of q, p, and possible time dependence, right? So let's just differentiate it, of course, straightforward. And again, I'm going to use that tensor notation. So I'm going to drop summations. So it will be partial derivative of h with respect to q and qi dot. Right? And then partial derivative of h with respect to pi dot. Right? And then, of course, partial derivative with respect to time, partial derivative of h with respect to time. And nothing else. All right. Okay, so now we are in the Hamiltonian formalism, right? So now we can start using our Hamilton's equation. So now they are under our belt, and of course we know that dh over dq, it's what? dh over dq, it's a minus pi dot. So minus pi dot. And of course, dh, partial derivative of h with respect to p, it's just a qi dot. qi I dot. As a result, you see we have minus P dot Q dot plus Q dot P dot. The first two terms go. And as a result, we have only partial derivative of h with respect to time. And so we used these two equations, but we still have this partial derivative of h with respect to time equals to minus dl over dt. So this is equal to, of course, minus partial derivative of L with respect to time. So we can write immediately, we can write so total time derivative with respect to time of h equals to minus partial derivative of the Lagrangian with respect to time. So again, if you start from the Lagrangian first in an attempt to move to the Hamiltonian, right? So if your Lagrangian doesn't have explicit time dependence, again, you can foresee the future. You can tell immediately that, okay, when I get to the Hamiltonian, my Hamiltonian is going to be a constant of motion, right? Of course, if Lagrangian doesn't have explicit time dependence, right? And of course, the same if you have Hamiltonian, if it doesn't have explicit time dependency, of course, you can tell immediately that Hamiltonian is going to be a constant, which is kind of first can be surprising because look, Hamiltonian, of course, depends on Q's and P's. And of course, we know that Q position of the system lives, right? Of course, Q changes with time. P momenta, right, also changes with time. System, I know, some parts accelerates, decelerates, right? So of course it lives, right? Everything changes in time. But somehow, if it doesn't have Hamiltonian or Lagrangian, doesn't have explicit time dependence, then all the changes in Q somehow balanced by changes in P. Every time they balance each other out all the time, giving us a constant H all the time, right? Which is interesting, right? So only you can change Hamiltonian if there is an explicit time dependence. You see T, okay, yeah, it means that your Hamiltonian is going to be, it's going to change as system lives, as system evolves, right? Which is quite interesting. Right? All right. So now I can sort of short summary. So I can write if L doesn't have explicit time dependence on T, then of course Hamiltonian is going to be a constant of motion. And of course I can write here H as well, but okay, and probably I should also write H varies with time only through the explicit time dependence, what I just told you, right, a minute ago. Right. And let me write this as well. So H varies with time only through its explicit time dependence. Only through its explicit time dependence. T dependence. Okay. Let me check what else I was planning to mention. All right. Yeah, and of course, we can combine this result with that result. So if now, if you start from the Lagrangian, for example, and you're trying to make a move into the Hamiltonian formalism, right? So if L doesn't have explicit time dependence, you can say immediately H is constant. And then if you look at the Lagrangian and you see this is correct and this is correct, you can immediately tell that your Hamiltonian is a total mechanical energy and it's a constant of motion, right? So of course, sometimes both of these, if both of these are correct, of course, H is E and equals, no, H is E and it's a constant. Yeah. Okay, so now after this, let's look at a simple example. central force. Right. All right, and after this example, we will derive these equations from the first principle as it should have been done in the first place, strictly speaking. So which part I can start erasing? All right, I guess I will, yeah, you have in your notes, right? And of course, I need it all almost, right? But something needs to be erased anyway. So, example. So, point mass, right, exposed to a central force. Right? No constraints, nothing like that, right? So M moves in a plane. And of course, immediately we restrict ourselves to two-dimensional situation, right? So which way I wrote? M moves in a plane, right? And exposed to the central force V. So we have central potential, central force, central potential, central force. One of the simplest example, right? And just in order to demonstrate these transformation procedures, this and that, and this, I mean. Right. So Lagrangian we can write immediately, right? In the previous chapter we spent probably like half a class getting to that Lagrangian, right? And now we're experts in that. Of course, we can write it down immediately. So L equals to m over 2, right? R dot squared plus R squared phi dot squared. I think I used phi, not theta. Phi, yeah. And minus our central potential. So the Lagrangian. And so we want to get Hamiltonian and then write down Hamilton's equations. Just to see that we're going to get exactly the same like what we got in the previous chapter. All right. Of course, we will have to construct our pseudo Hamiltonian first, which is the function of q, q dot, and t. And then, of course, we're going to prepare ingredients to replace q dots with generalized momenta. So, of course, our pseudo Hamiltonian, it's a function. Okay, let me put summation. So it's the variable which we want to remove, variable which we want to introduce, and minus old function. Right, Legendre transformation, all the time the same. It's as a result, it's easier to remember this, right? So old variable times new variable minus the old function, and all the time Legendre transformations are constructed like that. Okay, so now let's prepare those ingredients which we need to replace q dot with p, and of course that is done through the generalized momentum. So let's write down generalized momentum. Right, so it's a step number 1, now step number 2, right? So I'm using the method number 1. Maybe I should say that it's a method number 1, right? First method, which is slightly longer. Okay, so all right, so now we need to use expressions for generalized momentum, right? Okay, so we have two variables r and phi, so we're going to have two equations like this, pr and p phi. So let's start with pr. P sub r, it's a partial derivative of L with respect to r dot. R dot only here, so it will be m r dot only. And so now we're at this point. Now we need to invert it in order to get q dot, in our case r dot, in terms of r and pr. But in this case, just in terms of pr, r is not there. Right, so now invert. inversion. So r dot equals to p sub r divided by m. Okay, so first equation ready to be used. And now the second, because we have also phi dependence. So p sub phi, okay, it ugly phi. P sub phi equals partial derivative of L with respect to phi dot. Phi dot only over here, so it will be mr squared phi dot. Mr squared phi dot, and of course inversion will give us a replacement. Phi dot equals to p sub phi divided by mr squared. Okay, so now all ingredients are ready, and we need to write down this explicitly and start replacing q dots with p. Right. Okay, so h equals summation. In this case, of course, it will be over all variables from 1 to 2 in our case, because we have p and no, we have r and phi. I mean r and phi. So it will be r dot p sub r plus phi dot p sub phi and minus the Lagrangian. So Lagrangian is there, so let me just rewrite it in a bracket. So it will be m over 2 r dot squared plus r squared phi dot squared. It's kind of procedure is tedious, right? Not very pleasant. Straightforward, but and of course minus v as a function of r, right? Okay. So right now it's still pseudo Hamiltonian, written in terms of r dot phi dot, right? So not ready completely. So I can actually put a tilde on top. But now we have prepared ingredients, so of course we can shove them in our D here and then here, right? And of course phi dot will go only here. No, also there. Right. Okay. So the final push, right, to the victory, and yeah, I need to just insert them. So it will be p r squared divided by m, it's this, then plus p phi squared over mr to the power of 2, and then minus, okay, let me keep brackets and then I will. So we will have p squared over m squared. This m with one of those m's in the denominator will be cancelled, so we'll have p squared over 2m, 2m, yeah. So it will be p squared over 2m, okay, p sub r squared, right? And then similar should be there, right? So p squared, it will be m squared, this m squared, and this m squared, and then one m will go. So we'll have p phi squared over 2m r squared. So it will be plus p phi squared over 2m r squared. Right. And minus v. Innocent v, just sitting there doing nothing because it has the proper dependencies.
Don't the r squares cancel out? Do you
have
have r squared?
No. Here we'll hold it. No. Here when you square it, you will get power of 4. And then r squared also here, right? So of course, two r's will be downstairs. Okay, so you see we have here basically this and this, almost the same except for factor of 2, right? And this is with minus, this is with plus. So as a result, I can drop the tilde. Okay, now I can write explicitly what h depends, not just q and p. Now we have r and phi's. So r phi, then p sub r, p sub phi. There's no time dependence because it wasn't here in the first place. There's no explicit time dependence. As a result, we can tell immediately that h is the constant of motion, right? And of course, h is not going to have time dependence. And of course, that's what we're getting, of course, right? And so it is equal. And again, you see there's no tilde on top because now this is the final Hamiltonian. So it will be PR squared over 2m. Again, this guy with that guy give us just positive, and over 2m. And again, this positive, this negative, again, they will partially cancel each other. So p phi squared over 2mr squared. And yeah, plus. And then plus v. Minus, we're going to get plus, right? So plus v as a function of r. So final Hamiltonian. Final Hamiltonian function. Again, as I said, a little bit boring, these transitions, right? Getting through all this. But that's how it works. And it's a kind of fail-proof method, right? Because the second method, it's kind of slightly shorter because you don't have to subtract these terms. But at the same time, you have to be careful, you have to analyze properly so that you wouldn't make a wrong assumption and apply a method which might not work here. Right? But here it doesn't matter which system you have. If you want to make a transition from L to H, there it is. Drag yourself through this procedure and sooner or later you will end up with the correct Hamiltonian, right? But anyway, so now let's discuss the second approach. You know what? No. Let me finish. Let me write down Hamilton's equations, right? And then we're at the end, when we finish discussing the problem, we will look at this sort of second approach, which is slightly short. Let's just keep rolling. Since we started rolling in this problem, so now let's write down this point Hamilton's equations, and then at the end the second method, right? All right, so I will put a new bullet, and now our Hamilton's equations. First, I will write them in general. Qi equals, okay, Qi dot partial derivative of h with respect to pi. And again, these are first order differential equations. Order has been reduced. And the second, pi dot equals to minus partial derivative of h with respect to qi. Since we have two variables, we're going to have two these equations and two of those. All right, so let's start with the first one. So first r. So it will be r dot equals to partial derivative of h with respect to p sub r. H with respect to, okay, p sub r, it's only here, so it will be pr divided by m. P sub r divided by m. So equation number one. Less troubles with each equation, but now we doubled them, of course, relative to the Lagrangian formalism. So now phi dot equals to partial derivative of h with respect to p sub phi. Oh, wow. Okay, let me just write down all these four equations, and then next class we will finish this. So p sub phi, all right, so it will be p sub phi over mr squared. P sub phi over mr squared. So equation number one, equation number two, then equation number three, it will be p dots, p sub r dot equals to minus partial derivative of h with respect to r minus barely visible. Let me make it thicker. So r is here, and there are two places. So when we differentiate these 2 will disappear, minus will pop up, and power of 3. So it will be p sub phi squared over mr to the power of 3. Right? And we need to differentiate our potential. So minus dv over dr. Again, this minus comes from the equation. Here minus disappeared because of after differentiation we had another minus. Right? Partial derivative, straight derivative doesn't matter because v depends on r only. And force of habit, I wrote down partial derivative. Right? So, and the last equation, number 4, p phi dot equals to minus partial derivative of h with respect to phi, and phi is cyclic. Again, we're going to use the same terminology, cyclic or ignorable if a variable is not explicitly present in the Hamiltonian, so it's called cyclic. Phi in our case is cyclic. Right. So this is 0, and of course, as a result, immediately the corresponding generalized momentum, of course, in this case, it is going to be linear momentum, is a constant of motion. We can give it a name L, right? So p sub phi L equals a constant. Okay, so now we have tons of equations, and now we just need to, okay, at this point, we can forget that Hamiltonian treats R, for example, and PR as linearly independent. Now we have just a bunch of differential equations, and we need to solve for R and phi. Right? Of course, we know now we should recall that p dot is a derivative of p and r dot is a derivative of r. So now we will start messing up, combining all these equations in order to get what we wanted. So after this, it's just a calculus, right? So at this point, of course, after this point, Hamiltonian formalism is basically over, right? We use that physics, right? Okay, guys. So. Next class, we will just combine them quickly, just a couple of minutes, discuss the second method, yeah, and derive, I thought I would be able to derive Hamilton's equations from the first principle, from the Hamilton's principle. So we will do it next class. And after that, we will discuss advantages of Hamiltonian approach versus Lagrangian, and Lagrangian versus Hamiltonian, under which conditions. And then we will try to use advantages of both methods. We will try to create some kind of hybrid method, which is going to use advantages of Hamiltonian approach and advantages of Lagrangian approach. It doesn't give you any deep understanding of dynamics of the system. It doesn't give you a deep understanding of physics, but from the mathematical point of view, it's nice to get all the pluses from all methods, right? So we're going to discuss what is called the Routh procedure. Okay, so that's the near future, right? Next class.